Hello everyone, welcome to our discussion of section 8.1 where we will talk about sequences and their limits. Now before we see some examples in this context, we will look at a number of definitions and theorems involving sequences. These are very helpful when we try to answer questions about divergence and convergence of sequences. So as you can see on the screen, a sequence A sub n has some limit L when the sequence approaches L as n approaches infinity. In other words, we can write the limit of the sequence in that fashion. So if this limit of a sequence exists, the sequence converges. Now, right now, this might seem pretty straightforward definition, but please be careful when we get to series in section 8.2, which is coming up next, in the next video. Because in the series, if the sequence does have a limit, it doesn't necessarily mean that the series converges. If the sequence has a limit as n goes to infinity, then the sequence converges. We know that. But this does not tell anything about series, which will build on the concept of sequences. So this is a pretty critical thing to remember. As far as the sequences are concerned, if the sequence has a limit as n approaches infinity, the sequence converges, otherwise it diverges. But with the series, this isn't the case. Okay, we will look at that when we get to section 8.2. Now, limit laws for sequences, we've already seen these and applied them to functions, right? But sequences are not functions. There is a relationship between sequences and functions, but the two are not the same. So here are some of the limit laws that apply to sequences. None of this you really need to memorize because they're so straightforward that it's intuitive. We can intuitively remember these. We don't really have to commit these to memory that much. They're obvious. I mean, look at this one. Limit of the sum of two sequences as n approaches infinity is equal to the sum or the difference of the individual limits of the sequences. So this is pretty obvious, but we have it here just in case in your notes. For the case of your notes, so for the sake of your notes, I'm including them here. So here, if you have a limit of a sequence that is multiplied by a constant c, that constant can be pulled out and placed in front times the limit of the sequence as n approaches infinity. And then also the same thing that we showed that applies to the summation and difference between two sequences. Here it's applied to the product of two sequences. So the limit of the product of the sequences is equal to the product of the limits of the sequences. Okay, all of this is pretty obvious. Limit of a constant as n approaches infinity is equal to the constant itself. The same rule that we talked about applying to the multiplication and the sum and the difference of sequences also applies to the division or a ratio between sequences. The limit of a ratio of the sequences is equal to the ratio of the limits of the sequences. Okay, as n approaches infinity, given of course that this limit in the denominator is not equal to 0. And here we have the limit of a sequence raised to a power is equal to the limit of that sequence raised to the power. So the power applies to the limit of the sequence as well, given these conditions, that the power should be greater than 0 and the sequence should be greater than 0 or something positive. So p should be the power should be positive value. Okay. So there's more theorems and definitions that we have to look at before we can do some examples. The squeeze theorem that we saw applying to functions, to the limits of functions, here also applies to sequences. So your book has a really nicely done graph, and I just copied it here in these notes. So if we have three sequences, and I should maybe, because of the background, so maybe I should, that's better. So if we have three sequences such that AN, BN, CN, such that BN is in between these two sequences, or greater than A sub n and less than or equal to sequence C of n, then if the A of n has a limit as n approaches infinity, which is equal to the limit of sequence C of n, let's say some value L, then the sequence in the middle, in this case B sub n, has a limit that approaches to the same value. And this is a graphical depiction of that same concept. So you have C of n that is coming down here, approaching some value L. Maybe I should draw some line here indicating that is L, something like that, like this, maybe, or maybe just, because it's already too cluttered, this drawing, I'll just put an L here. Okay, now if AN approaches L, the limit of AN approaches that, if the limit of CN approaches L, then the sequence BN in the middle will have the same limit L as n approaches infinity. If in this theorem, if limit of the absolute value of a sequence is equal to 0, then the limit of the sequence without the absolute value as n approaches infinity is also equal to 0. This is pretty important and useful theorem, and for this case, I've shown this example, which is showing where we can apply this theorem. And in a number of examples, this will come in very, very handy. So if you have a sequence like that, minus 1 to the n power divided by n, obviously as n becomes odd or even, this minus 1 will change the value of the sequence. It will change the algebraic sign of the sequence, right? So if you calculate the limit of the absolute value, which means if you disregard this minus 1, if you just calculate the limit as a positive 1 over n as n approaches infinity, whatever that limit also applies to the entire sequence. So you can take the absolute value of the sequence, calculate the limit of it like that. You can treat the limit like that, as if it was just positive 1 divided by n. And if it's equal to 0, then the limit of the original sequence, which had negative 1 to nth power, also is going to equal to 0. So it's a very useful theorem here. The continuity and convergence theorem, this is also very helpful in a number of occasions as we solve problems about sequences, whether they converge or diverge. If function f is continuous at some L, again, functions and sequences are not the same thing. So let's consider some function f that is continuous at some value. And if the limit of the sequence as n approaches infinity also equals to that same value, then we can calculate the limit of the function in that sequence, and that will be equal to the value of the function at L. Because the limit of the sequence as n approaches infinity equals L, so that will be the same thing as if evaluating the function at L. Okay, we will make use of this theorem in our examples. It's one of those theorems that connects sequences and functions and how they can be used together. Okay, so in this case, this is again one of those very useful, maybe I should mark these. Definitely this one, I will highlight it. If the sequence some r to some power is convergent, or the sequence, not if, but the sequence this is convergent if this base or r varies between -1 and 1, greater than -1 and less than or equal to 1, and divergent for all other values of the base r. Okay, so the limit of that sequence, the limit of the sequence as n approaches infinity equals 0. So it's converging. It's equal to 0 if the base is somewhere between -1 and 1. And it approaches 1 if r equals 1. Okay, very useful. Another theorem that's very useful for us in the examples that are coming up. So in this definition, so we've already looked at the concept of functions that are increasing or decreasing, right? This is similar definition applied to sequences. So a sequence a sub n is increasing if any term, if any subsequent term in the sequence is always greater than the previous term in the sequence for all values of n greater than or equal to 1. N basically represents the position of a number in the sequence, which we saw a basic introduction of in pre-calculus 1 or Math 126 if you took that course here. So n refers to the order in which that number appears in a sequence, which this n greater than or equal to 1 basically means if for any two terms in the sequence, if the next term is bigger than the previous one, then you can conclude that sequence is an increasing sequence. And it is called decreasing if the next term, a sub n plus 1, is less than a sub n. So if the next term, which is identified by this subscript n plus 1, if the next term is less than the previous term for all numbers in the sequence, that's what this means, n greater than or equal to 1, then you have a decreasing sequence. So a sequence is monotonic if it is either increasing or decreasing. So either one of these, if you have either one of these sequences, it is called a monotonic sequence. And then also this one, this is again one of those identities or definitions that relates sequences to functions. If the limit of a function as x or the independent variable approaches infinity equals L, and the value of the function at n equals the sequence, then the limit of the sequence is also equal to that value, the limit of the function. So if the function at n is equal to the sequence, in other words, if you substitute in the function that has x as its independent variable, if you replace that x with n and you end up with the sequence, that's what this top line is saying, then the limit of the sequence is going to be the same thing as the limit of the original function as x went to infinity. Okay, so replace x with n. If you end up with the same with a sequence, then the limit of the function as x approaches infinity is equal to the limit of the sequence as n goes to infinity. There are more definitions. These are all good because they come in handy as we solve problems. So if a sequence is less than or equal to some value, let's call it capital M, for all members of the sequence. That's what this means. If the sequence is less than or equal to some value for all members of the sequence, then the sequence is bounded above. In other words, it has a ceiling. It has an upper bound, which we call bounded above. The sequence is bounded above. If there is a value, if the sequence is larger than or equal to some value for all members of the sequence, then the sequence is bounded below. So there is a value that is lower than all values in the sequence, and that's identified by the lowercase m. These are simple conditions to, by the way, remember. So if the sequence is bounded above and below, then the sequence is a bounded sequence. In other words, if you have a sequence that is just bounded above or bounded below, we can't call that sequence bounded. A bounded sequence is one that is both bounded above and bounded below. That's what this statement is saying, or this definition is saying. And finally, for monotonic sequence theorem says that every bounded monotonic sequence, remember, bounded sequences are the sequences that are bounded below and above. Every bounded and monotonic sequence, monotonic meaning it's either increasing or decreasing, the sequence is always convergent. So if we have a sequence that is monotonic and it's bounded below and above, then the sequence for sure is convergent. Here are a couple of notes here I thought would be useful. Not every bounded sequence is convergent. See, remember, because we just said if the sequence is bounded and monotonic, then it's convergent. But if the sequence is just bounded above and below, which means that the sequence is bounded, it doesn't necessarily mean that the sequence is convergent. For example, this sequence, this simple sequence here, simple but useful, right? This is a very useful example to demonstrate what this statement is saying. The sequence will range between -1 and 1, right? As you change this n from 1 to 2 to 3 to infinitely many odd and even powers, this sequence value jumps between -1 and 1. So we know that the sequence is bounded, right? It doesn't go beyond these two lower and upper boundaries, but it's divergent because it oscillates between these two values. It doesn't converge into to any one of those, but it just oscillates back and forth. So that's, again, grounds for calling this sequence a divergent one. So not every monotonic sequence is convergent either. So these conditions should be true, and they should be true at the same time. Every bounded monotonic sequence is convergent, but individually they're not sufficient for us to conclude that a sequence is convergent. So not every monotonic sequence is convergent. Here is a sequence, right? A sub n equals n. So obviously the a sub n will approach infinity as n approaches infinity. So it's definitely divergent. Okay. So now let's take a look at some examples that help us apply these definitions and theorems. So here's the first problem. We want to find, find a formula for the general term an, and I should write the problem statement here. So we have a sequence shown in this way, and the first term is 1, negative 1/3, 1/9, and negative 1/27, 1/81. And so this is an infinite sequence. So given this of the sequence, well, they want us to find a formula for the general term a sub n of the sequence. So we are given a few members of the sequence, and we're asked to find the general formula for it, assuming that this pattern of the first few terms continues. Well, we know that this is A1, right? So this is A1, this is A2, or the second term, first term, second term, third term, fourth term, and fifth term. And clearly there are a couple of patterns emerge right away. One is the fact that the algebraic signs alternate. So let's make a note of that. Note algebraic signs alternate, and for the first term it's positive, for the second term it's negative, for the third term again positive, for even terms it looks like then for even terms it's negative, for odd terms it's positive. Okay, so those signs alternate. Okay, so now we have to capture that pattern in some kind of in our sequence. Also, notice that every term after this one is a multiple of 1/3, right? So 1/3 times 1, 1/3. If we ignore or disregard the algebraic signs for a second, 1/3 times 1/3, 1/9. 1/9 times 1/3, again 1/27, and so on and so forth. So then 1/3 is part of the pattern in the sequence. So if we note that, so also each term is minus 1/3 times the preceding term, right? That's another pattern. So if we capture these two patterns in a nth term expression for the sequence, so we'll have, for sure we should have minus 1/3. Then that should be raised to some power such that if we begin with n equals 1, we get something positive, or 1 in this case. So that would be, and then for n equals 2, we get negative 1/3. So that we can get by putting our power as n minus 1. So now we can test this. Usually I would approach with these problems with a pile of scratch papers, and I would try several scenarios and see which one gives me all these terms. So and we can say for n greater than or equal to 1. Okay, so this would be our answer for that problem. So now we can test it. I've already tested this, but if I had a new sequence, I would go through and test to make sure that all these terms are the result as I go through different values of n. So if n equals 1, we get 0 power minus 1/3 to 0 power is 1. If n equals 2, we get 1. 2 minus 1 is just 1. Minus 1/3 to power 1 is minus 1/3. If n equals 3, then the power would be 2 even, so that would cancel this minus, and we'd get 1/3 squared, or 1/9. If n equals 4, that would be, the power would be 3. 4 minus 1 would be 3, so minus would stay, which we would expect it to stay right there. And then 1/3 to third power would give us the minus 1/27. And the same thing is true for the next term. If you replace n with 5, you'd get positive 1/81. So in the next example, it says, in each case below, find the limit of the sequence and determine if the sequence converges or diverges. So let's begin by first example, and we want to start with this sequence. A sub n is equal to 3 plus 5n squared over n plus n squared. So in calculus 1, we had a technique for finding the limit of rational expressions when we dealt with functions and x variable and so on. Remember what that technique was? It was divide. We can treat this portion of this as such function, and then we can apply that technique, which was divide each term in the numerator and the denominator by the highest power of the variable in the function, and here the n, the highest power of n in the denominator. So we can apply the same technique. So let me just remind you that this is that technique, dividing every term by the n term that has the highest power. In the denominator. This is what we're going to get. We're going to get, so each one of these divided by that, 3 divided by n squared. That's obviously n squared in the denominator, right? That term has the highest power in the denominator, plus 5n squared divided by n squared, n divided by n squared, plus n squared divided by n squared. What do we get? Well, let's simplify this. We get 3 over n squared plus 5 divided by 1 over n plus 1. Now let's take the limit of this piece after we've applied this technique. So we have, so taking the limit of 3 over n squared plus 5 plus 1, as n goes to infinity, then that piece, 3 divided by infinity, is simply 0 plus 5. This piece is 0 again as we divide 1 by infinity, plus 1, so 5. So the sequence has a limit and it converges. Okay, so the sequence converges to 5. Okay. All right, so let's do another example. So in this example, we have this sequence, h sub n equals tangent of 2n pi divided by 1 plus 8 times n. So we had, if I look back, notice that we had a theorem or a definition, this one. Notice that we said that if in this continuity and convergence theorem, if the function f is continuous at L and if the limit of the sequence is equal to L, then the value of the function at L is equal to the limit of the sequence as n goes to infinity. So then let's consider this, the argument of this function. The argument of this, if we look at this tangent as a function, for a second disregard that this is a sequence, consider this as a function, and this being the argument. Let's see, let's find the limit of the argument of that function. Okay, so first, we will find if the argument of the function has a limit. And if it does, then the sequence has a limit which is equal to the the limit of the function at that value. So we will find if the argument being this portion, has a limit. So we're going to take the limit of that piece, the inside the parentheses, 2n pi divided by 1 plus 8n as n goes to infinity. Okay. Again, we will apply the method we applied to this previous example. So we're going to take the limit while we divide all the terms in the numerator and the denominator by the highest power of n in the denominator, which is simply n. So 2n pi divided by n divided by 1 over n plus 8n over n. Okay, so what do we get? We will get n and n simplify. This n and this n will simplify. We will get 2 pi divided by 1 over n plus 8. Okay. Now, if we apply the limit, we will get 2 pi divided by 0 plus 8. So this is equal to pi over 4. So in the sequence, the inside the parentheses has a limit that whole term has a limit that is equal to pi over 4 as n goes to infinity. Okay, so then, so we know that so by the way, the tangent function at pi over 4, if this has a limit that is equal to pi over 4, then the tangent, what happens to the tangent function at pi over 4? It is continuous, right? And it's equal to 1. So let's make a note of that. So then I'll just write it here. The tangent function is continuous at pi over 4. So by the continuity, this was one of the theorems we had, continuity and convergence theorem. We know that the limit by, well, that was on page, I think, 3 or something like that. Well, page 2. So the limit of the function as n goes to infinity is equal to the function at that value. So the function and the sequence will have the same limit. So let's apply that then. We have limit of the tangent of 2n pi divided by 1 plus 8n as n goes to infinity is equal to the tangent of the limit of that function, that expression, which we evaluated to be pi over 4. And divided by 1 plus 8n. Okay, so the limit of our sequence, this being our sequence, this whole thing, the limit of the sequence is equal to the tangent or the function evaluated at that limit, which was pi over 4. Okay, so tangent of pi over 4, which is equal to 1. So the sequence converges. Converges to this. Okay. All right, so let's do another example. Suppose we want to know if this sequence converges or diverges. That one. Okay. I want to remind you that to please pause, give this some thought, and write a solution on your scratch paper, and then unpause the video and see if your solutions agree with this. So that would be a good exercise as you watch through this video. So I want to begin by first separating the constant part of this sequence from the sequence part, or the non-constant part of it. So I will say a sub n, we have 3 to n power times 3 squared, right? We can decompose this or break this up into this over 5 to n power. Now this 3 squared is just 9, right? So we can write that as the sequence as being equal to 9 times 3 to n power divided by 5 to n power. Furthermore, we can put this 3 over 5 to n power on the outside. So we can write this as 9 times 3 over 5 to n power. Now recall one of the useful theorems we had, or I guess definitions or theorems that we had, we just mentioned a few minutes ago, was that, so I'll just say recall that a sequence r to some power converges if, do you remember what the condition was? If this base r is between -1 and 1. So if r is between -1 and less than or equal to +1. Okay, so that will come in. So that's certainly the case here. So 3/5 is, which is the r, the base of that power, it's somewhere between -1 and 1. So we can conclude that that sequence converges. So then let's continue with finding the limit of the sequence, knowing that it's going to converge. So we have the constant can stay on the outside, and then times, and I guess that there should be an arrow from here to here. So limit of 3/5 to n power as n goes to infinity, that's equal to, so the constant is out here, let me not forget about that, and this approaches 0 as n goes increasingly large, approaching infinity. So because this quantity is between -1 and 1, it will always approach 0. And so 9 times 0, we move this up a little bit, and so we have 0. So this sequence converges to 0 as n becomes or approaches infinity. Converges to that. Okay, so another example would be suppose we have this sequence a sub n equals square root of n plus 1 divided by 9n plus 1. Okay. Well, again, please pause the video, spend no more than 10 minutes or less to find the answer to this. See if it converges. If it does, find the limit of it, or find the limit and see if it converges, and then come back to the video. Okay, so I'm going to take the limit of this sequence using the technique we learned back in Calculus 1. So limit of the sequence as n approaches infinity would be equal to the limit of that plus 1. Let's divide each term under the square root by the highest power of n in the denominator. That would be just n. Everything is under the square root, so that's just dividing every term by n. And so we get, under the square root, we get 1 plus 1 over n. We get 9 plus 1 over n. So when we apply the limit, these two terms drop out as 0. So we will get square root of 1 over 9, or 1/3. So the sequence does converge to this value. So the sequence does have a limit, which is that. So the limit of the sequence then converges to that. Converges to that. Okay. So this was an easy one, right? Another example, suppose we have a sequence that is -1 to n plus 1 power times n divided by n plus square root of n. Okay. So let us then take the limit of this piece. We will worry about this piece later, because this piece of the sequence is simply going to create terms that are alternate in algebraic sign, right? So for an odd number terms in the sequence, if n equals 1, 3, 5, 7, we will end up with an even power when we add 1 to it. So this minus drops out. So we get, for odd numbered terms in the sequence, we get positive values. But for even numbered terms in the sequence, such as the second number, the fourth number, the sixth number, and the eighth number, and so on, we will get an odd power when we add 1 to it. So this -1 is preserved, and we will get negative terms in the sequence. That's all. That's all what this is doing. So first, let's find the limit of the rest of the sequence, excluding this piece that affects just the algebraic sign. So we have limit of that, n divided by n plus square root of n. In this case, note that the highest power of n in the denominator is this, which has power 1. This one is just 1/2, so this is the 1. And so that would be equal to, so let's divide each term by n. And that would be, so this would be this divided by n as well. And then so after simplifying, we need to, so limit as n goes to infinity, we have 1 over 1 plus, simplifying this, we get 1 over square root of n, right? So because n is square root of n times square root of n, this piece in the denominator. This n is square root of n times square root of n. One of those square root of n cancels with that. We end up with 1 over square root of n in here. So now, if we apply the limit as n goes to infinity, this term drops to 0. So then we get 1 over 1 plus 0, and we get 1. Okay, so we found that this portion of the sequence does have a limit as n goes to infinity, and that limit is equal to 1. Now, that piece that we didn't consider, this -1 raised to that, is just going to change terms to, it's going to alter. So it would seem that the sequence has a limit, right? And it does. But because of this, we have a special circumstance where the terms are going to oscillate. It's going to oscillate, the limit is going to oscillate between -1 and 1 as n goes to infinity because of that. So this whole sequence as a whole, it's going to diverge. So let me write this down actually. So considering the piece that we didn't originally, considering -1 to n plus 1 power, the sequence approaches 1, when n, or positive 1, when n equals 1, 3, 5, and so on, right? Because for these values of n, we get an even power which cancels this negative. We get 1. And let me just add ... odd numbers for n equals any odd number. And the sequence approaches -1. Approaches -1 when n equals 2, 4, 6, or any even numbers. This oscillating behavior always means that the sequence is divergent. Between 1 and -1, the sequence diverges. Okay, like that. In the next example, we have a sequence like this. Cosine of 2 over n, right? So now this, as we take the limit of this sequence as n goes to infinity, obviously the argument of cosine approaches 0, right? So let's quickly write that down. We know that as n goes to infinity, then the argument there, 2 over n, goes to 0, right? And the cosine function is, of course, continuous at 0. Continuous at 0. In fact, we have cosine of 0 equals 1. Okay? So by continuity and convergence theorem, or by continuity and convergence, I don't think it's a theorem, but it's an ax, or it's an identity that we use. By continuity and convergence, the sequence converges. Converges to 1. Okay. Well, it is a theorem, actually. I just looked it up. So it is a theorem. theorem. Okay, so some of these, as you can see, are very simple and quick to solve. Another example would be this one. If we have a sequence that is the inverse tangent of n divided by n. So as we take the limit of this, remember that one of the first things that we discussed, if we take the limit of this, right, limit of a sequence that is a ratio, we can break this up into limit of the numerator by the limit of the denominator, right? We can do that. So then if we do that here, we will, if we say, again, please pause the video and see what answer you will get, and then you will come back to see what solution I have. But that way it would be better if you do your own work also on a piece of paper. So taking the limit of the sequence in this case, as n goes to infinity, we have right, we have this scenario, and then we can also break this limit up to the limit of the numerator divided by the limit of course, as, let me put it in a different color so it stands out, as n goes to infinity, and here also as n goes to infinity of n. So now, from trigonometry, or Math 127, if you took the course here, recall what the inverse tangent graph looked like, right? Let me actually do a quick graph of the inverse tangent, just as a reminder. So recall the graph of inverse tangent of x, right? So it was then we have the y-axis here. And then we have a horizontal line that represents positive pi over 2 as the horizontal asymptote. So this is y equals positive pi over 2, and another horizontal line here that is y equals minus pi over 2. And then the graph of the inverse tangent was something like this. So, like that, right? So as x approaches infinity, the value of the inverse tangent, and so this is the inverse tangent of x, approaches pi over 2. Okay, so we can make use of that. So this numerator then, as n goes to infinity, this numerator approaches pi over 2. Right, so I'm just going to start from here, below the graph, I'm going to start from this, right? Thus, I just drew the graph to remind you of that. And so, thus the limit of n would be equal to pi over 2 in the numerator, and of course this will be just infinity. So pi over 2 over infinity, we will get 0. So the limit of this sequence, so this sequence, as we take the limit of this sequence, it converges to that, to 0. Therefore, the sequence converges. So converges to that. Okay. So remembering this from trigonometry simplifies this quite a bit. It's just inverse tangent approaches pi over 2 as x or n approaches infinity. All right. Let's do another example. Suppose we have this sequence 2 to negative n power times cosine of n pi. Okay. So let's use this negative power to convert this sequence into a fraction. Okay. Again, please pause the video and see how you would approach this. Spend no more than 10-15 minutes and then do the best you can and then come back to the video. Hopefully our answers agree. So the sequence would be equal to cosine of n pi divided by 2 to n positive power, right? If we write it in fraction form. Now we know that it doesn't matter what n value is. The cosine of n pi, it's going to oscillate from negative 1 and 1, right? This is something we know from trigonometry. So let me write that down. So note that cosine of n pi, it's going to vary between negative 1 and 1. Okay. So then if we take the absolute value of this, we can write that cosine of n pi varies between 0 and 1. Okay, so thus or therefore the absolute value of n pi is going to vary between 0 and 1. Okay. Now we can divide, because this quantity is positive, right? 2 to the n power is a positive quantity. So we can divide all sides of this inequality by 2 to the n power. So let's do that. So by 2 to the n, we have, what do we have? We have on that side, we have 0 divided by 2 to the n, and absolute value cosine of n pi divided by 2 to the n, and of course 1 divided by 2 to the n power. So let's simplify this a little bit. On the left we simply have 0. In the middle we have that. 2 to the n. And on this side we can write this as 1 over 2 to n power, right? So now remember that little identity or theorem that we had. Maybe I can dig it up again. That says that if you have a sequence r to the n, right there on page 3, if we have such sequence, this sequence is convergent if r, the base, is between -1 and 1, and divergent for all other values of r that fall outside of this interval. For r between -1 and 1, that sequence converges to 0. For r equals 1, it converges to 1. Okay, so we have this case. So we know that this side is also this side is already 0. This side, we know by that identity that it's going to be 0 when we take the limit of it. In fact, let me write that down. So, well, let me take the limit of all sides. So we have limit of the constant 0 as n goes to infinity, and then limit of this quantity as n goes to infinity, and of course limit of as n goes to infinity. So we know that this side is 0, this side is 0. So we know by the squeeze theorem that the middle also should go to 0. So let me simplifying here. We have like that. And then so then from by the squeeze theorem for sequences, right? By the squeeze theorem for sequences, then the limit of that must also go to 0. As well. But we have another theorem, right? Our original sequence didn't have the absolute value, right? It didn't have the absolute value, but we do. So what does that say? What does this result say about the original sequence that didn't have the absolute value? Well, we had another identity. Let me see if I can find it. Hopefully I can. That right here on page 2 this time, that says, this theorem says that if you have the limit of an absolute value as n goes to infinity equals 0, then the limit of the original sequence as n goes to infinity goes to 0 as well. So we can use this result to our advantage and conclude that the original sequence that didn't have the absolute value will also go to 0. So I'm just going to make a note of that here. Make a note of this here, and also here, that knowing by theorem that if limit of an absolute value of a sequence as n goes to infinity equals 0, then limit of the sequence itself as n goes to infinity must be equal to 0 as well. Thus, so therefore, limit of cosine of n pi divided by 2 to the n as n goes to infinity equals 0 as well. So this is what the sequence converges to. Converges to that. Again, this is so important that even though we haven't gotten to 8.2, I want to remind you, this is, if a sequence has a limit, then the sequence converges, but this doesn't say anything about the series. The series is the summation of all the terms in a sequence, which we will get to in 8.2. So if the limit of a sequence that comprises a series has a limit, if the sequence that comprises a series has a limit, it doesn't mean that the series converges or diverges. We have to investigate that. But this is just a reminder. When we get to section 8.2, we will look at that in detail. Here's another example. Suppose we have a sequence that is equal to one plus sine of 2n divided by 1 plus square root of n. So just like when we were dealing with the cosine of 2n pi, let's focus on the numerator. We know that the sine function varies or ranges between -1 and 1, right? So, and I hope you paused the video already. If not, I'm just reminding you. So knowing, pausing to do your own work, of course. So knowing that the sine of 2n varies between -1 and 1, then we can write that the absolute value of that sequence, so we can write, absolute value of a sub n must vary between 1 over, or be less than or equal to 1 over 1 plus square root of n. And of course, if you remove the absolute value, what does it mean? It means that, so thus, the sequence without the absolute value would be greater than -1, knowing that the numerator varies between -1 and 1, we can write the same result as the sequence being between -1 over 1 plus square root of n and +1 over 1 plus square root of n. Okay, so this one is really easy. If you take the limit of both sides, what will you get? Well, let's do that really quickly. Limit of the left side as n goes to infinity. I'm sure you're already seeing that this limit goes to 0, right? Because the denominator is going to be very, very large. So -1 over that, it's going to be 0. And then on the right side, we have the same situation with the +1 over that. So on the left we have 0, on the right we have 0. So I should, let me add it here. Limit of this sequence as n goes to infinity limit of the sequence as n goes to infinity. Okay, so by the squeeze theorem, the limit of the sequence must also go to 0. For sequences, then limit of the sequence as n goes to infinity must also go to 0. So the sequence converges to that, to the limit of the sequence, right? Converges to that. Okay, so another example. So we have this sequence a sub n equals natural log of n squared divided by n. Okay, so what happens if we apply the limit to this as n goes to infinity? I'm sure you'll find something familiar. So let's do it. So the limit of a sub n as n goes to infinity so sorry, this parentheses should end here. I will fix this before posting these lecture notes on Canvas. So this power belongs to the numerator, as you can see here. So this parentheses, this part of it should be erased. I'll do that before posting this on Canvas. So if we take the limit of this expression, then what will we end up with? We get infinity divided by infinity. So do you remember what this represents? It represents a case, it's an indeterminate case, where we have to apply the L'Hopital rule, right? So we must use L'Hopital's rule. Okay. So let's do that. So L'Hopital rule, and I'm going to convert to x, so we're dealing with the function version of this sequence. So limit of natural log of x squared divided by x, right? So I just replaced n with x as x goes to infinity, of course. So in this case, we already decided that we want to use the L'Hopital rule. So to do that, we're going to take the limit of the derivative of the numerator divided by the derivative of the denominator. So we have limit as x goes to infinity of, take the derivative of this, 2 times natural log of x times the derivative of natural log of x by the chain rule is 1 over x divided by, of course, the derivative of x is just 1. Okay, so this simplifies to just 2 natural log of x over x. So I'm just going to put the 2 in front like that, and then natural log of x divided by x. So if we apply the limit, what will we get? So once again, we will get 2 times, again, infinity over infinity, right? So do you remember what we need to do at this point? we'll have to do apply the L'Hopital rule again, this time to that. So we must use because this is again an indeterminate case of a limit. One of those several cases, almost a dozen cases where we have to use the L'Hopital rule. So we must use the L'Hopital's rule again. Okay, so this time to that. So limit of would be equal to limit of this derivative of the numerator would be 1 over x, denominator would be 1, and so we will get, so this is just uh, 1 over x, of course. So apply the limit, we will get 0. Okay, so now, and I wrote that here, so let me L'Hopital's rule again. So recall the other identity that we had. We had another identity that, let me bring, I think it was on page 3. So if I bring that back, we had this identity that if limit of a function equals L and the function evaluated at n, so if you replace the x with n, and if you get the sequence, and the function we already know as x goes to infinity has a limit, and it's equal to L, then the limit of the sequence as n goes to infinity equals to the limit of the function. Okay, so we're going to make use of this. Recall that if the what did we have? If we limit of the as x goes to infinity equals some value, and this is pretty critical, so there is an and condition here, and if you replace the x with n, you get the sequence. So the function at n is equal to the sequence. Then limit of the sequence, limit of the, I should say, not the function, but the sequence as n goes to infinity equals to the same thing, L. So we did that for the function, and we got 0. That means the sequence, in this case, if you replace x with n, of course, you get the sequence that we already had. So we've satisfied all the conditions for applying this theorem or identity, like that. And so thus, the limit of the natural log of n squared as n goes to infinity divided by n also equals 0. Converges to that value. Okay. All right, so let's do, I guess, let me see, do I have another example? So this is a different example, but it's different than what we've done so far, which is good. We'll see a different type of example. Here we want to determine is increasing, decreasing, or not monotonic. And we want to answer, is the sequence bounded? So here's one example. Okay, so when we talked about increasing and decreasing sequences, remember that we talked about, if I can find it here in one of my notes here, let me see if I can find it so I can show you. Let's see, it should be somewhere. Sorry for that. I'm trying to find. It's no big deal if I can. Let's see. Limit converges and diverges. So there it is, right there on page 3 again. Okay, so a lot of these good theories and definitions are on page 3. So when we talked about increasing, that means that for all the terms in the sequence, every next term should be larger than the previous term. For the decreasing sequence, every next term should be less than every previous term. So that's on page 3 if you want to refresh your mind about that definition. So speaking of that, then we have a sub n. Then let's calculate a sub n plus 1, because that's part of the definition, right? When we're determining if a sequence is increasing or decreasing, we're going to have to find a sub n plus 1 as well. So if we do that, and we can replace n with n plus 1 to find that, what do we get? We get 1 over 2n if you distribute the 2 and then add plus 5, right? So this piece is an plus 1, an we already had it. So looking at the denominators of these two, the denominator of an plus 1 is larger than the denominator of a sub n, but the numerators are the same. That means that this quantity is always less than this quantity. So let's write that down. We know that 1 over 2n plus 1, which is an plus 1, less than 1 over 2n plus 3. And let me just remind you, this is an plus 1, and this is an, right? An plus 1 is less than a sub n. So when in this case happens, we have a decreasing sequence. Thus, an is a decreasing sequence in this case. Then the question is it bounded or not? Well, let's see. If we look back at this sequence, n, remember, n starts at 1 and goes up to the higher positive integer, right? So n is going to vary from 1, 2, 3, 4, 5, all the way to positive infinity. So because this is a fraction, the largest value of this fraction happens when n equals 1. For every next value of n, this value becomes a little bit smaller, a little bit smaller. So the largest value of this sequence happens when n equals 1, or 1 over 5. 2 times 1, 2 plus 3, 5. So we can actually write that as we go along. Note that the largest sequence is obtained when n equals 1, right? Where the sequence is going to be 1 over 5. Okay, again, just substitute for n with 1, you get 1 over 5. What about the smallest value? So we can say from this statement, where I'm going is that it is bounded. It is bounded for sure above. It is bounded above. Let's see if it's bounded below. If this n approaches infinity, of course the sequence approaches 0. So this sequence is also bounded below. Okay, so that's one note. And then let me add another. So the smallest value, we talked about the largest value. The smallest value of the sequence is when n goes to infinity, right? Where a sub n approaches 0. So from these two statements, the sequence is bounded below and above. So therefore, the sequence is bounded below by, I should say actually not equal, but greater than. It will never be exactly equal to 0, but it will approach it, of course. So n greater than 0 and less than or equal to 1 over 5. Okay, for all n greater than or equal to 1. Okay, so so the sequence is also bounded. So this is to answer the original question that they asked us. So an is decreasing sequence. We answered that question. Then they asked if the sequence is bounded. Yes. So thus the sequence is bounded, as we've shown here. And so I'll just put an arrow to that. Okay. All right. So let us do maybe another example of this kind. So again, this is in the same context of the previous problem. So I'm just going to call this part B, when our sequence is equal to 2n minus 3 divided by 3n plus 4. Okay. So again, please pause the video if you haven't already, and work on this 10-15 minutes and see whether you find, is this decreasing, is it increasing, is it bounded? Answer those questions and then come back to the video again. Okay, so I'm assuming you've done that. So in this case, let us create a function with x replacing n, and then find the derivative of it. So in this case, that would be a good approach. So So we know that for this function, then we can find the derivative, or the derivative is as follows. So we have 2, the derivative of the numerator times the denominator minus the derivative of the denominator times everything in the numerator divided by, of course, the denominator squared. Like that. So what do we get? If we, and by the way, this is f prime of x. So if we distribute everything and simplify, we get 6x plus 8 minus 6x plus 9 divided by 3x plus 4 squared. So we get the derivative f prime of x is equal to, these two cancel each other out. We get 17 divided by 3x plus 4 squared. So this derivative is always positive, which means the function is continuously increasing function. So let me make a note of that. So note derivative f prime of x is positive for all values of x. Right? Because of that, the function that represents that, the antiderivative of this, is always increasing. Thus, it's an increasing function. But the function is really, we have a case where the function and the sequence are the same thing. Okay, so let me and therefore, thus the sequence is an increasing sequence. Okay, so that's that. Increasing sequence. So that partially answers the question they asked. And the other one is the sequence bounded? Okay, so if we replace the n, you know that n varies from 1 to infinity. So if we plug in for n with 1, so let me, so the sequence, let me just title this sequence boundedness. Okay, so this is what we're investigating now. To do that, for n equals 1, what do we get? We get 2 times 1 minus 3 divided by 3 times 1 plus 4. And So we get minus 1 over 7. And then, so then if we replace this with 2, we will get 1 over 2. So we'll get something positive, 2 over 10. And so that would be larger number. So this would be the lower bound. So we have, in this case, and this will be the only negative number in this sequence. So this would be the lower bound. And then n goes large. And so let's see. So we can make a relative comparison here. And the upper bound we can set that as, let's say so so the sequence, so let's see, an equals 2n minus 3 divided by 3n plus 4. We can say that this is less than 2n minus 3 divided by just 3n, right? We've just made the denominator smaller. The numerator we kept the same, but made the denominator smaller. So for sure, this quantity, it will always be larger than that. But this quantity, it's going to be small itself. It's going to be less than 2n or 2 over 3 or 2n over 3n or 2 over 3, right? Because we've made the numerator larger. When we transition from here to here, we've made the numerator larger. So this quantity will always be larger than that, and this will always be larger than that because of the denominator, the difference in the denominator. The denominator was made smaller, so this will always be larger than that, and this will always be larger than that because here the numerator was made larger, right? Here it's always less than 3, minus 3, but we've taken that away. So the numerator is larger, and therefore this quantity is always larger than that. So the sequence is definitely bounded above and by some quantity, right? So so the A, and thus, oops, sorry. I was off the screen for a moment, I think. I apologize for that. But so according to that then, let me explain because I don't know if my screen, my page was on the screen. So in this transition, this is the original sequence. We know that this quantity has to be larger than this because we took away the 4 from the denominator. So we made the denominator smaller, but the numerator stayed the same. So this quantity will always be larger than that. Here, we made the numerator larger because we took away the minus 3. So this quantity, or the simplified version of it, 2/3, will always be larger than this. So definitely the original sequence is bounded above by some value. So thus an is bounded below and above. And thus, and so an is bounded. Okay, remember, a sequence is bounded only if it is bounded both below and above. So this, we're not required to show what is the upper bound. We're just showing that here we found the lower bound. We could find the exact value, but the upper bound, we showed that it has an upper bound. So that's all we care about. It's bounded above, It's bounded below, therefore the sequence is bounded. So this wraps up our discussion of section 8.1, which was an introduction to our to the topic of sequences. And next, in section 8.2, we will look at the series, which is simply summation of the terms in the sequence. And in that section, we would want to know whether a sequence is divergent or convergent, as we discussed here for the sequences. All right, thank you for watching this video until this point. I hope it was worth your time. And for now, have a nice day, and I'll see you again next time.